Okay, so in last lecture we have seen this example of paging, and then we have seen the effective memory access time, all right, to measure the performance, and we have seen this translation look aside buffer and how to find out this effective memory access time. So this equation we have derived, and then we have seen what is the impact of high heat ratio and low heat ratio that we have seen, right? And then we were discussing something about page table size, right? So the page table size is a concern because the page table reside in your memory, right? So more page size means it will occupy more space of your memory. Now the page table size that depends on how many pages you have, right? Because the number of pages in your logical address space means that much entry will be in your page table, right? Total index you can consider. And if we want to reduce this entry, what we can do, we can increase the page table size, right? So increasing in page table size may create a problem in a last block, or it will create an internal fragmentation in that, right? And if you reduce the page table size, then obviously it will increase the number of entries in your page table, right? So what we can do? So we were discussing the example, right? So in university you have so many students, right? And in one file you store the details of all the students. Then whenever you need to find a particular student, what you need to do, you will open that file, and from that file what you will do, you will search that student, right? Okay, now instead of that, what we can do that in university we have different institute, right? So we are dividing the whole file institute wise, right? So CSPIT, PDPIS, MBA, right? So different institute we have, I2IM, that is MBA, right? So based on that, we are dividing our file, right? And when we want to search a student, right? First, from Charuset, we will see whether it is of CSPIT or some another institute. Once we know that, we will search that student detail in particular file only, that is CSPIT. So in this case, I will search in two files. First, the university, which indicates me that in Charuset CSPIT is there, so students is belong to that CSPIT, so it will redirect me to the CSPIT file, and from CSPIT I will search that student. So here, whenever I need to search a student of CSPIT, I need to load that university, the compact file now, and the CSPIT, not the I2IM, not the DevStar, not the MCA, right? This different file I need not load. But in the first case, all the students are in one file only, so all the data I need to load. So it will occupy more space. So this thing is called multi-level paging, right? Multi-level paging. This is a multi-level paging, right? Now, what is the structure of multi-level paging, right? So first I will explain you the structure of multi-level paging, and then we will see the example. So the CPU, this is the CPU, it generates logical address, right? So this is your logical address generated by CPU. You have displacement and here you have a page. Same way, your physical address and you have a main memory, and here also you have a displacement. All right, so this is your page, this is your frame. Okay, so previously there is a one page table. From this page number we will search in that page table, and from that entry we are getting the frame number. Now what will happen that now that page table is divided in, and we are right now looking at a two level paging, right? So it is divided in two page table, not we can say two. So this is your outer page table and this is, you can say, inner page table, and right now I am showing you only one. Assume that the page size is 1 KB. Page size is 1 kilobyte, right? Page size is 1 kilobyte. Now the page table that you have, that will divide it in this page size. Right? So now we'll make a group of it. Page size of 1 KB. So assume that you have only one page right now, right? From here you are searching this index, from here you are getting the frame number, and you have this page table. So what you will do, you will start dividing this page. In this size 1 KB, right? In 1 KB that you will do, right? So this is the page size, and you divide your page table, that is page table size, with your page size, right? With your page size. So what you will get? You will get certain numbers. Right? So now in two level paging, your first outer page table will store the address of page table. This is a page table, outer page table. This is also page table. This is inner page table, right? And from here you will get the frame number. What you will get? You will get a frame number, right? But how to do this? So first, when this is generated, this thing will be generated, right? It will divide into two portions. Right? You can consider P1 and D1. You can consider P1, D1. Right? So P1, so it will find the index. Right? So if this is the index using P1, this is the index, right? P1, this is the index. Now from this entry, you will get a page table. From this entry you will get the page table, right? And in that page table, which entry that will be taken care by this D1, right? So in this page table, which entry, that is D1, that is D1, right? Because our whole page table, that is divided in 1 KB size. It is divided in 1 KB size, right? So what will be the D1? So in this case, D1 is 10. And if I take a 32 bits, right? This is a 32 bits, and my displacement, let's take displacement around 12. Okay, I'm just assuming that 12. Okay, so this is D1. So this is also, it's around 1K, that is 10. That is 10, right? So now your logical address is divided in 3 portions. First portion, P1 will search in the outer page table using index. It will find the entry and it will give the address of the next page table. What this page table holds? It holds the address of another page table, right? So suppose there is another page table, likewise, right? So it will store the address of this page table, starting address, right? And in that page table, which entry, that you will find out using D1, and from that particular entry you will get actual F. Your physical address will remain as it is, right? You will find out actual F from this. So this inner page table will store your frame number, this, but the outer page table, it will store the address of this page table. It will store the address of this page table. Any doubt in this?
No, sir.
Right? Or now assume that whenever I want some byte, particular byte, at that time what will happen? Which page table I need to load? Should I load this outer page table? This is only one page table, right? Outer page table, and all these page table, because here how many entries are there? 2⁻10 entries are there. So this will store the address of 2⁻10 page table, right? So 2⁻10 page table I need to load. Is it so?
No, sir, that's specific one.
No, right? So what I will do, it will load this first page table. And then from this 2⁻10 page table, it will load a specific page table which is required. Right? Suppose I require this page table. So this page table and this page table will be loaded. These two page table will be loaded, and you can see 2⁻10 entry, and here also 2⁻10 entries are there, right? Because D1 is 10 bits. So 2⁻10, 2⁻10. Assume that for simplicity, both have 4 bytes entry size. So this will be 4 KB and this will be also 4 KB. So how much entry? It's a 4 plus 4, 8 KB need to be loaded. But previously it was 2 raised to 20. 2 raised to 20 into 4. If it is only one page table, single level paging, then in that case your P is 20, means 2 raised to 20 entries are there in page table, and each entry size is 4 byte. So 4 into 2 raised to 20 bytes, that is 4 MB. That is 4 MB that you need to load. So instead of 4 MB, now we have reduced to 4 KB plus 4 KB, that is 8 KB. You can see we have reduced that. Right, so this is possible. This is possible with multi-level paging. Right? Any doubt in this? Then ask me. No? So let's just derive the effective memory access time. Right, as we have diagram here, so effective, and assume we have TLB as well. Right, and what TLB store? Logical address and physical address, so directly it will map. And this time you know C and M. C plus M. Right? So for 2-level paging, effective memory access time for 2-level paging, right? If it is without TLB, if I don't have TLB, then what will happen? First, I need to find in this, that is in memory. So M, then from this, I need to search in this bit table. This is also in main memory, M, and from that, I'm getting this physical address, right? So that is also in main memory, or that is actually memory only. So that is M. So that is 3M without TLB. And if I consider the TLB, then what will be the effective memory access time equation? So you know this, hit होगी तो TLB मिस होगी तो जो रेगुलर होगा वो, अगर हिट है देन क्या आएगा, TLB में जो एंट्री हम ढूंढ रहे हैं वो मिल गई, देन व्हाट विल बी हियर, यहाँ पे क्या आएगा, heat means what, you are getting the data in TLB. TLB एक्सेस टाइम क्या है, लास्ट में हमने देखा था C, TLB में मिल गया, यहाँ पे फिजिकल एड्रेस मिलेगा तो वो कहाँ पे सर्च होगा, मेन मेमोरी M, तो ये क्या आएगा,
C plus M.
yes, this is C plus M. And in case of means डेटा यहाँ पे नहीं मिला तो क्या होगा, तो क्या होगा, पहले यहाँ पे गया डेटा नहीं मिला, यस
C plus 2M.
C plus 2M. Again you can think C plus 2M. यहाँ पे गया नहीं मिला, राइट, सो ये काउंट होगा, फिर ये सर्च हुआ, फिर ये सर्च हुआ, उसके बाद ये मिला, ये होगा ना। यहाँ पे सर्च किया नहीं मिला तो यहाँ पे सर्च करेगा, इससे कुछ मिलेगा वो यहाँ पे जाएगा, यहाँ से कुछ मिलेगा वो यहाँ पे सर्च होगा, तो क्या हुआ?
C plus 3m.
Yes, this will be C plus 3m, or without, not without, in single level paging we have seen this C plus m plus 1 minus x. यहाँ पे क्या था? C plus
2m.
yes, it's a 2m, ऐसे था. Yes, so if I consider this is one level paging or only paging and TLB, right? So in general, if I need to write effective memory access time for n level paging with TLB, what I can write? X will be as it is, 1 minus x वो भी रहेगा, हीट के केस में तो ये पता ही है हमें C plus m ही रहने वाला है. मिस होगा तो ये भी हमें पता है कि ये C में तो एक होगा ही. ये जस्ट नंबर वेरी हो रहा है. ये देखो यहाँ और यहाँ पे कोई रिलेशन है, ये नंबर में और ये नंबर में कोई रिलेशन.
n plus 1 m.
Yes, that is n plus 1 m. Right, so this is the general equation, and without TLB if I need to write access time and level paging is equal to what? यहाँ पे क्या था? 2m, यहाँ पे क्या था? 3m, यहाँ पे क्या होगा? n plus 1m. This is without TLB. यही आएगा ये, क्योंकि TLB नहीं है तो ये सर्च ही नहीं करने वाला है. Right, so directly it will go like this. Right, and if your heat ratio is very low, then no use of TLB, right? It will perform worst, right? But most of the time that will not happen. Most of the time that will not happen. वो नहीं होगा, right? Because your OS, it will increase your heat ratio, right? It will store data such a way that it will increase the heat ratio only. Okay, any doubt in this, then tell me. Okay, just see this. Right now we are not jumping in the example. We'll do later on in next lecture. Just we will see this thing. What is the concept of multi-level paging? If this is a 3-level paging, right? So this logical address will be, right? You have a P that is divided in P1 D1. So again your P1 that is divided in P2 D2. Right, so again you have one table, from that you will get a one page table, and from that page table again you are getting the page table, and in that page table you have a frame number. Right, so what you decide the size, it depends on that. Okay, then this is the effective memory style, effective memory access, and we have generalized that thing as well in this two equation, right? Okay, so we will end our today's lecture here, and from next lecture onwards we will see the example on this, multi-level paging, and then we will move to segmentation, right?
Yes, sir.